Good morning, students, and welcome to today's session. So, we will continue with work by energy from where we left off yesterday. Uh, we had discussed about conservative and non-conservative forces in detail yesterday, and we understood that conservative forces are forces wherein the work done is independent of path, and therefore the work done in a round trip is always equal to zero. Whereas a non-conservative force is one where the work done is path dependent, and therefore in a round trip the work done becomes non-zero. And kinetic friction was the physical example we saw of a non-conservative force. So let us continue from that point onwards today. So we start with another definition today: potential energy. Generally, we denote it with the symbol U. Okay, so how do we define potential energy? And what do we define potential energy for? Okay, so first of all, we define potential energy for a system. Okay, instead of for a particle or for a body, we define it for a system. And potential energy is a form of energy that is defined on the basis of the state of a system or the configuration of a system. If, for example, if we're talking about potential energy of a spring, it has to do with the state of the spring in terms of how much it is compressed or how much it is extended. If you're talking about gravitational potential energy, it has to do with the position of the body in concern with respect to the surface of the earth. Because the potential energy is for the system consisting of the gravitational field of the earth and the body. So potential energy for any system is defined on the basis of the state of the system or the configuration of the system. So that's how we define potential energy. Okay? So potential energy defined for a system as the energy associated with its configuration or state. So on the basis of this definition, one way to one way to calculate potential energy or mathematically define potential energy is that whenever we want to change the state of the system or the configuration of the system, an external agent has to do work against the internal force within the system, and that work done is equal to the change in potential energy. So therefore the work done by an external agent in order to change the configuration or change the state of the system equals to the change in its potential energy. So now we can give an equation based on this. So the work done by the external agent will be equal to the change in the potential energy for the system, provided this is the work done change the state only. That is, the kinetic energy of the system is not changing, or the external agent is not doing any work against a non-conservative force. Okay. So let's now understand this in context of some examples. So for example, if we have a spring mass system, like this. Now, for this system, if the state of the spring has to be changed, that is, it has to be either compressed or extended, then an external agent has to do work against the spring force. That work, which will be the work done against the spring force, will be stored in the system as the change in potential energy. So just make a note of all this with the definition and the example I've given. Okay, so equation for, So in general, when an external agent does work to change the configuration of a system, this work done by the external agent is against the internal forces. So therefore, it is negative of work done by the internal forces. That is equal to the change in potential energy. So for example, when we are talking about the above system, the internal force for the system is the spring force. So this is, so now since delta U, that is final potential energy minus initial potential energy, is a path independent quantity, it is what we call a state function. It depends only on the state, the initial and final. Therefore, work done by internal force also must be path in, that means the internal force for a system must be conservative. Okay. If potential energy can be defined, a system, if it has internal forces which are conservative, then we can define something called potential energy for the system. If its internal forces are for some reason non-conservative, then we cannot define potential energy for such a system. Okay, when I, Arey Piyush, curl will come much later, yeah. That is a more advanced thing. Don't worry about curl right now. As I told you yesterday, first we have to define gradient. Curl is in fact not in your JEE syllabus also, but we will discuss about it. Okay, so it is conservative. Only in that case we can define the potential energy. Okay, so therefore the change in potential energy is defined as negative of the work done by internal conservative force during the change. So this is the relationship between the potential energy for a system and internal conservative force within the system. A system has potential energy, or it possesses the property of potential energy, only when it has internal conservative forces. And the relationship between potential energy and internal conservative force is this, that the change in potential energy, okay, this equals to negative of the work done, the system's internal conservative force. During the change in state. So this becomes the definition for this relationship. So this is extremely important. Okay, so make a note of this properly, and then we'll start understanding this with numerical examples. Yeah, Samar, the reason we cannot define for a system which has non-conservative forces, that will become clear if you read this line over here. Okay. When you look at this equation above the right hand side, delta U, it is a path independent quantity. We cannot define potential energy as something that depends on path, because potential energy is defined as the energy associated with state and not with path. So if potential energy change is path independent, then work done by internal force cannot be path dependent. We cannot equate a path dependent quantity with a path independent quantity. Yeah, Viraj, that is above over here. Na? When we are changing the configuration of the system, the work done by the external agent is the work done against the internal force. So that is why it is equal to negative of work done by internal force, and that is equal to the change in potential energy. Okay. Why an external agent has to do work in order to change the configuration of the system? Okay, he has to do it has to do work only because it has to go against the internal force within the system. If there was no internal force, then there would not be any work done to change the state of the system. No? So you have a block on a smooth horizontal surface. To move it, we don't have to do any work because there's no internal force. But to lift it to a certain height, we have to do work because we are going against gravity. Okay, so let's go back to our example of the spring mass system. So potential energy for a spring, how do we define that? Let's see. Okay, okay, so let's come back to potential energy of a spring. Now we will develop the formula for it from the definition. So imagine the situation where we have a spring mass system on a smooth horizontal surface, and we have to very gradually extend the spring from its natural length configuration to some amount of extension. So we have a block and we have a spring. Now the spring is over here at its natural length configuration. Now a gradually increasing force is applied by an external agent to very slowly increase the length of the spring from L to L plus E. So in that process, find the work done by the external agent, the work done by the spring force, and the change in potential energy of the spring as a result of that. So let's understand this. So what is happening here is that because the block is to be moved very slowly, okay, the change in kinetic energy is zero and there is no friction. So work done by non-conservative force is zero. And of course, it's moving horizontally. So work done by mg and work done by normal reaction will also be zero. So that means the work done by the external agent only changes the state of the system. Okay. So in this case, the work done by the external agent will be equal to negative of the work done by the spring will be equal to the change in potential energy of the spring. Okay. So this is just rewriting what we have already understood before, but in context of this particular example, So the external agent has to apply a force in such a way that it's very slowly increasing. You can't suddenly apply a large amount of force, because otherwise that will result in the kinetic energy of the block changing. And the force has to be applied horizontally, so you're not giving it any vertical lift or going against gravity or anything. You're only applying that force for one purpose, and that is to very slowly increase the length of the spring from L to L plus A, where A is some constant, let's say. So in that case, the work done by you as an external agent, that will be equal to the potential energy stored in the system, or that will be against the internal force of the system, which will be the spring force. And therefore we will get this relation, that work done by the external agent is equal to negative of work done by spring force is equal to the change in potential energy of the spring. So just write down up to here, then we'll execute this calculation over here. Okay. So of course, here we understand that spring force is a conservative force. We've already seen that yesterday. And that is why it is possible to write an equation like this. Any system where the internal force for some reason is non-conservative, we cannot define potential energy in the first place. Yes, very slowly. Na? We've already said that the block has to be moved extremely slowly. So its speed is tending to zero. That's why the change in. Okay, so next up, let's see how to do this calculation exactly. So as we are increasing the length of the spring, or as we are pulling the block, okay, from its initial position of x equal to 0, or natural length of the spring, to the final one, at some intermediate stage, let us say the spring is having an extension of x, where x is less than a right now, but it's greater than 0. So at this point of time, remember our block is being moved very slowly. So the acceleration of the block is tending to 0, the velocity of the block is tending to 0, and the forces acting on it are the external force and the spring force. It will act like this. So first of all, the free body diagram of the block will show us that since the acceleration is 0, the external force at any instant has to just about balance the spring force. So the magnitude of the external force has to be equal to kx. So that's why we said that the external force is a gradually increasing force. Okay, as x increases from 0 to a very slowly. So accordingly, from point to point, our force has to be incremented or increased very slowly. Okay. Now during this change, suppose the block moves by a small displacement dx. Okay. So during the small displacement dx, which I've shown, the work done by the external agent is F external into dx with a positive sign. So from this equation now, you can see that that is equal to plus kx dx. Okay. The work done by the spring force is minus kx dx, because the spring is, you can see, the direction of the spring force is opposite to the direction of displacement. Okay. So now we can see that for x equal to 0 to x equal to a, the total work done by the external agent will be equal to integration of this. So that is from x equal to 0 to x equal to a, from initial to final state. So the work done by the external agent in this case is plus half square, and that will be exactly equal to negative of the work done by the internal conservative force. Okay. So work done by the spring force, that you know as a formula only, is minus half k a square, because finally our x is becoming a. So when we put the limits, it will be half k a square. So you can see over here that what is happening is that by definition, the work done by the external agent is negative of the work done by the spring force, which is equal to the change in potential energy of the spring. So the change in potential energy of the spring is plus half k a square. Okay. For initial x being 0 and final x being a, this becomes our change in. Okay. So you see that if we apply work kinetic energy theorem to the block, we say that net work done is equal to change in kinetic energy. So work done by external agent plus work done by the spring force should be 0. Okay. And if we apply work energy concept to the spring mass system, we will say that the work done by the external agent equals to the change in potential energy of the spring. Okay. Because external agent is doing work such that only the configuration of spring is changing. In this case, the work is being done taking care that there is no change in kinetic energy, and of course there is no work done by non-conservative force because there is no spring present. So now compare this equation and this equation, and again justifies what we were talking about earlier, that delta U is negative of the work done by the spring. The relationship between internal conservative force and the change in potential energy is given by this. Okay, so just if you to understand this whole thing, so during this extension, from L plus A, at some intermediate time when the state of the spring is like this, This is how we do the calculation of each of these things. So just start by understanding the calculation of work done by spring and work done by external agent. Then we will come back to this. These two things. Start by understanding and noting down the calculation of these two. Exactly, Viraj. So for the work done by the spring, we can directly use the formula we discussed earlier. It's minus half k into final position square minus initial position square. So here we can use the formula. Yeah, Shikhar, see the first equation, you're just calculating the work done by the external force now. So in the diagram above, you can see the external force is acting in the direction of displacement. So F dx is the work done during a small displacement. Okay. Now the magnitude of the external force is equal to kx because the acceleration of the block is tending to 0. So that is why the work done by the external agent is plus kx dx during the small displacement. That is work kinetic energy theorem. Na? Net work done is equal to change in kinetic energy. So on the block, what is the net work done? It is the work done by the external agent plus the work done by the spring, and that should be 0. Okay. Okay, good, Shikhar. Okay, so now that this particular example is understood, so through this example we have understood what, that if we are extending a spring from natural length to an extension of x, sorry, or whatever, the change in potential energy is plus half kx square or plus half ka square or whatever. Okay, so now let's understand a general formula for potential energy of a spring. So we have for any change of state from x equal to some initial position to x equal to some final position of the spring, okay, delta u is equal to negative of work done by the spring. Okay, so we already have this formula. Now delta is nothing but final minus initial. So final minus initial potential of the spring. Now for work done by spring, we already have the formula. This we have seen this formula before. So comparing both the sides, you can see that this quantity is equal to half k x final square minus half k x initial square. So the absolute potential energy for a spring is defined as half kx square. So this is the potential energy for a spring as a function of its state, that is x. Yeah, and we have already defined earlier the work done by spring force. We have seen this earlier. In any situation, integration of kx dx from initial to final. So that is minus half k, sorry, minus kx dx. So it is minus half k into x final square minus x initial square. Now we are just adding the definition over here that we've learned above. The definition of potential energy is what? That delta U is negative of work done by internal conservative force. So change in potential energy of a spring is nothing but negative of work done by a spring. We're just applying this definition over here. It's very simple to understand. X is the state of the spring, no beta. X is the state of the spring. So we always define X as positive X as the extension of the spring, negative X as the compression of the spring. Okay, so next we will define gravitational potential energy. So gravitational potential energy. Now remember I told you potential energy. So you haven't written down. Okay. Okay. So talking about gravitational potential energy, we always define gravitational potential energy for a body of a certain mass. Okay. We can denote this with the symbol UG. Okay, so this is defined for a body or particle of mass m in with respect to its position from the Earth's surface. So that is the configuration of the system. The position of the body with respect to the Earth's surface, that is a configuration. So when defining, okay, Devansh, okay. So when defining the potential energy, the system that we talk about, the system for which this potential energy is defined is the mass plus the Earth's gravitational field. And the state of the system or the configuration of the system will be the position of the mass with respect to the Earth's surface. Okay. Now, as far as definition is concerned, it's very easy. The change in gravitational potential energy is going to be negative of work done by gravitational force. This is coming from the fact that for any system in general, delta U is negative of work done by internal conservative force. So here, for this system, the gravitational force, that is mg, is the internal conservative force. So the change in potential, gravitational potential energy equals to negative of work done by gravitational force during that change. Okay. So this becomes the definition. Now this is even easier to calculate because mg is a constant force. Okay. Unless we go to extremely big heights compared to the Earth's surface, like a height of few thousands of kilometers, then mg starts becoming a variable force. But here we are dealing with regular mechanical systems at the Earth's surface. So the heights we are talking about is very nominal height of few meters or at max a few hundred meters. So the gravitational field is uniform. So for this chapter, we will treat gravitational potential energy in context of very small heights with respect to the Earth's surface, nothing close to 1,000 kilometers. So our formula for gravitational potential energy change will be very, very easy. In the later chapter of gravitation, we'll see that it is a bit more comparable. Yeah, Shikhar, if you remember in Newton's laws long ago, we had discussed how the acceleration due to gravity varies with height above the Earth's surface. So if you go to a height of few thousand kilometers or even a few hundred kilometers, your gravitational force or weight of an object will start to decrease because the distance from the surface of the Earth is much larger. So the gravitational pull of the Earth becomes less now. Okay, so now let us see the formula using this definition. So we've seen that if we define the y-axis as a vertical, y-axis is the vertical axis, then mg for any body as a vector is minus mg cap. Okay. So work done by mg is mg dot s. So if a body is going via any kind of path from some initial to final position, because gravity is a constant force at the surface of the earth, it becomes this. Okay, so the work done by gravity just becomes mg into delta y, where delta y is the change in the y coordinate. So it is y final minus y initial. So the coordinate of the final position is x initial y, sorry, x final y final. The coordinates of the initial position was x initial y initial. Then during this change, during this displacement, this is going to be the work done by mg. So delta u being negative of work done by the internal conservative force, delta u becomes minus mg delta y. This is the formula we have for change in gravitational potential energy, where delta y is the change in the vertical coordinate. So here, this is change in gravitational potential energy for a body of mass m undergoing a vertical displacement of delta y. Okay. So this formula is limited to situations where we can treat small g to be a constant. So delta y should not be large compared to the radius of the earth. Oh, just a minute, people. This one comes with a minus sign because this is like this, no? Just correction here. Because Because here now we will write the displacement as delta xi cap plus delta yj cap, or x final minus x initial plus y final minus y initial. Now when you take the dot product of mg as a vector in this, now there is a minus sign involved. So in this dot product there is minus mg delta y. So the work done is minus mg delta y. So the change in potential energy is minus of this. So it becomes plus mg delta y. So this is the formula for change in gravitational potential energy when a body of mass m is going through a vertical component of displacement of delta y. Okay, so basically from this formula we can understand that if delta u is mg delta y, where we understand that y is the vertical coordinate. So it means that if a body displaces such that its height increases by h, then delta y will be plus h. So change in gravitational potential energy will be plus mgh. So in order to increase the height of a body through whatever path, but if I'm going from this initial position to this final position where the height is increasing by h, okay, then the change in gravitational potential energy is positive. Okay. Whereas if a body's height is decreasing, Yeah, so just a minute, I'll reshare the screen. Yeah, so in the case of gravitational potential energy, it is actually not even the displacement that matters, it is only the vertical component of displacement that matters. If the vertical component of displacement is positive, that means we are increasing the height of a body from the surface of the earth. In that case, the change in gravitational potential energy is positive. We are increasing the gravitational potential energy. Whereas if the body's height is decreasing from the surface of the earth, it's coming down, then the gravitational potential energy decreases. The delta U is a negative quantity. So just make a note of this. This is an important rule of thumb to remember. The rest of the formula is very simple. Okay, so hope this particular formula derivation is clear to you. So now at this point of time, these are the two particular types of potential energy that we'll be applying in the further applications of work energy theorem. Okay. The general definition of potential energy for us is okay. It will always be for any system delta U is defined as negative of work done by the internal conservative forces. Okay, or you can also write this as minus of F internal conservative dot ds from initial to final position. This is the general definition. But in particular, we will see that elastic potential energy of a spring, okay, we will always use the direct formula. Spring potential energy is half kx square. So change in potential energy for a spring in any situation will be half k into final position square minus initial position square, and gravitational potential energy for a body with respect to the surface of the earth, the change in gravitational potential energy is equal to mg delta y, where delta y is the change in the y coordinate, is the change in the vertical coordinate with respect to the earth's surface. Okay. So this second formula that we have for gravitational potential energy, this is a bit of what we call a working formula right now. It is not the absolute formula. For the absolute formula, we will learn more about gravitation later. So that's why we are not defining the absolute potential energy. We are just defining the change in potential energy. And we have that conditional statement over here that this is applicable only for the situation where delta y is very, very less compared to the radius of the earth. Okay. But that's not a problem here because the radius of the earth is 6,400 kilometers. So unless we are going to a height of at least a few hundred kilometers, we don't have to worry about the absolute formula. We go with this working formula. Okay. Now next thing we will see is the application of the concept of potential energy in what is called work energy theorem. Okay, so this is the main theorem for this chapter. Work kinetic energy theorem that we had studied earlier was like, you can say it was like a part one of this theorem, but this is the more general theorem. So unlike work kinetic energy theorem, work energy theorem is defined for a system. It is not defined for a single body. Okay, so work energy theorem is defined for a system. Okay, for example, a spring mass system or a system consisting of a body and the Earth's gravitational field, something like that. Okay, so the statement of work energy theorem is that the work done by external agent plus work done by non-conservative forces like friction or air resistance or anything like that is equal to the change in kinetic energy of the system plus the change in potential energy of the system. This is the statement. And collectively, the kinetic energy plus potential energy is also called the mechanical energy of the system. The sum of kinetic energy plus potential energy is called mechanical energy. So you can also say that work done by external forces plus work done by non-conservative forces equals to the change in mechanical energy for the system. So in this work done by any external agent on the system. This is work done by any non-conservative forces. Example, friction. So if there is any non-conservative force present in our system and is doing work, okay, then the sum of this, the work done by the external agent plus the non-conservative force, is equal to the change in kinetic energy plus change in potential energy. Yeah, Shikhar, I have written it down for you, the work energy theorem. So the work done by external agent plus work done by non-conservative forces equals to the change in mechanical energy for the system. Okay, so let us look at how we can apply this in various situations. So for example, we have something like this now. Okay, so on a smooth frictionless surface, we have that spring mass system. Okay, so the spring constant is given to us, let us say, as 25 newtons per centimeter, and the mass of the block is, say, 2 kilograms. Okay. Now, initially, the spring is relaxed, so x is equal to 0, and the block is at rest. So initial speed of the block is 0. Okay. Now, at t equal to 0, a constant horizontal force of magnet, let us say 5 Newton, starts, oh sorry, 50 Newton, let's say. And we'll take the mass of the block as, okay, let it be that. Okay. So 50 Newtons starts pulling the block to the right. So first of all, calculate the work done by this force and the change in potential energy of the spring as the block moves through a displacement of x. Next thing, calculate the kinetic energy of the block as a function of x, and from that find the speed in meters per second for the block at x equal to 1 centimeter. So by the time the block is displaced by 1 centimeter, we have to calculate what is the speed of the block. Okay, so just understand the question first, and then we will look at the application of work energy theorem here. Okay, so you'll realize that if we apply work energy theorem and all the formulae that we've discussed above, This is actually just a formula based question. Don't really have to do any kind of derivation or any kind of equation framing here. We have to just use the formulae and substitute the values. So what's happening is, the moment we apply this horizontal force on the block, but remember it's a constant force that we are applying. It's a constant force of magnitude 50 newtons. The spring is of constant 25 Newton per centimeter, and the mass of the block was 2 kg. Now the initial state of the spring was that it was at natural length. So we can take this as our x equal to 0 position, and the initial speed of the block was 0. So now by the time the block has moved from here through some displacement x, so it's moved from x equal to 0 to some x equal to positive of x, the spring has also extended by the same amount. Okay, and continuously the same amount of force is acting. So the block would have developed some speed v. So the first part is very easy. The work done by F will just be F into x. Now because F is a constant force. Okay, so the force is F I cap and the displacement is x I cap. So work done just being dot product, just positive of Fx. And the change in potential energy of the spring, you just use the formula half kx square, because x final we'll take as x initial as 0, and we'll just use the formula. Okay, so as I said, the first part is just formula based. Now second part, to find the kinetic energy, just take your system as the block plus the spring. Okay. So on your system you can see that the spring force is internal conservative force. So the spring force kx is the internal conservative force. Okay. Then normal reaction and mg are external forces. But you can see work done by mg is 0. Work done by normal reaction is 0. Work done by F is Fx. Okay. And non-conservative forces are not there. So no friction. So that implies that work done by non-conservative forces will be 0. Okay. So if we take our system as this, we will say that work done by external agent plus work done by non-conservative force should be change in kinetic energy plus change in potential energy. This is the general statement. So here, this will become work done by F only. Non-conservative force is not doing any work. This should be equal to the change in kinetic energy plus change in potential energy of the spring. So this is our effective work energy theorem now. That F, whatever work it is doing, it's resulting in some change in kinetic energy plus some change in potential energy of the spring. So this is our application of work energy theorem. Okay. And now we have to just substitute. So going from this state to this state, what is the work done by F? It is plus Fx. What is the change in kinetic energy from 0 to V? So it is plus half mv square. What is the change in potential energy? The initial x was 0, the final x is x. So it is plus half kx square. So this is the relationship between the three. So you can see from here that half mv square, which is the kinetic energy, as a function of x is f into x minus half kx square. So this is the kinetic energy as a function of x, the position. Make a note of this. Okay, so now for the last part, we have to find the speed v when the extension becomes 1 centimeter, right? We have to find the speed v when the extension becomes 1 centimeter. So let's just substitute the values here. Okay, find v at x equal to 1 centimeter. So half mv square. Now the mass of the block was 2 kgs. Okay, is equal to F. So the force was 50 newtons into X, which is 1 centimeter, so 10 raised power minus 2 meter, okay, minus half K. Now K was 25 newtons per centimeter. So 25 into 10 raised power 2 newtons per meter into 10 raised power minus 2 square. So V square is becoming zero point 0.5 minus half into 25 into 10 raised power minus 2. So V square is 0.5 minus 0.125. So V will become square root of 0.375 in meters per second. Alright, so hope this question is clear. Now let's look at another type of typical example. Now next, let's say we have a situation like this. we have an irregular slope kind of situation, and then that finally ends in a smooth track. And at the end of the smooth track, attached to the wall is a spring like this. So what is happening is that a block is being released from some position here, such that this position is at a height of h with respect to the horizontal section of the track. So, so a block of mass, let's say 5 kg, is released from rest from the position A on a smooth track as shown. So first of all, given that h is equal to 20 meters, find its speed at the point B on the track. As it slides down to the point B, what is the speed of the block? And secondly, given that the spring constant is, let us say, 10 newtons per centimeter, find the maximum compression the spring will experience after the block impinges against it. Impinges means after it pushes against it. Yes, Aditya, that's correct. Very good. Now work out the second part. Yeah, 20 meters per second is the correct velocity. Now, what about the compression? So you can see here that going from A to B, okay, and then from B to, let's say, another position C, where what is happening is that the spring is developing maximum compression. So at the moment when the spring will have maximum compression, the speed of the block will be zero. X will be maximum. Okay. So let's say that is the position C. So now if I go from, so if I take my system this time as the block plus this spring plus the Earth's gravitational field. Okay. So I can see for this particular system, what is happening is my mg and spring force, they are both internal conservative forces. So for them, I will consider spring potential energy plus gravitational potential energy as my net potential energy. Whereas normal reaction, it is the only external force. But work done by normal reaction is zero. No friction. So therefore, work done by non-conservative force is also zero. So work done by external agent is also zero. Okay. Work done by non-conservative force is also zero. So in my work energy theorem, they should be equal to change in kinetic energy plus change in potential energy. So in this case, so there is this relation that change in kinetic energy plus change in potential energy is zero, or we can say change in mechanical energy is zero. So this is a situation where we can say that for this particular system that we have chosen, for this system, mechanical energy is getting conserved. That is the change in kinetic energy of the block plus the change in gravitational potential energy plus the change in spring's potential energy is zero. Okay. So this makes things very simple. Whenever we have mechanical energy conservation, we can solve the problem completely by formula based method only. Because, okay. So now you can see from A to B here, what is happening. Change in kinetic energy is plus half mv square. Change in gravitational potential energy is minus mgh. And change in spring's potential energy is zero because you're not doing anything to the spring. So you're converting the loss in gravitational potential energy to an increase in kinetic energy. So your V is becoming square root of 2gh or 20 meters per second. So that makes things very simple. Now next, when you're going from B to C, so at B you had kinetic energy of half mv square. At C that is converted into elastic potential energy of the spring. So going from B to C, you're moving horizontally, so there's no change in gravitational potential energy, but you're losing all your kinetic energy and converting that into spring's potential energy, whatever that maximum extension. So minus half mv square plus half k x maximum square is zero. So this was your first equation. This is your second equation. Now we can make life even simpler by comparing the two. So from equation 1 and 2, you can see that half mv square is equal to mgh is equal to half k x maximum square. So you can write x maximum like this also. It is square root of 2 mgh by k, or that is the same thing as b into square root of m by k. If I go with this, it is 20 meters per second to square root of mass of the block was 5 kg and k was 10 Newton per centimeter. Like this. Okay. So this is the simple application of work energy theorem over here. And as you can see, in situations where mechanical energy is conserved, the application of work energy theorem becomes even easier. But the condition for mechanical energy to be conserved is that work done by external agent should be zero and work done by non-conservative forces should be zero. So the left hand side of the equation, the work done side should be zero. So that on the right hand side, the change in mechanical energy is zero. That means the mechanical energy is constant. Okay, so that concludes this week's session. So this is the point up to which you have to prepare for the upcoming test on 20th. Okay, up to the simple understanding of work energy theorem and the formula of potential energy of spring and potential energy of this thing, gravitational potential energy. Yes, Durgesh. So see here again what is happening in this particular system that we have taken, which is the block plus the spring plus the Earth's gravity. Mg and kx are internal conservative forces. So for them we consider potential energy, this term. These are internal conservative forces. So we don't consider them on the work side. We consider them on the potential energy side. Whereas the only external force which is acting on the block therefore is the normal reaction which is not doing any work. And there's no friction. So work done by non-conservative force is also zero. So when you write the statement of work energy theorem, on the left hand side you can see the work done by external force is zero because normal reaction is not doing work, and there's no non-conservative force, no friction present. So the other term is also zero. So left hand side of the equation is zero. No? So that means the change in kinetic energy plus change in potential energy is zero, or the change in mechanical energy is zero. So that is the meaning of the term conservation of mechanical energy. If the change in some quantity is zero, then that quantity must be conserved. So that is the concept we are applying over here. Mechanical energy is conserved in this situation. Is it clear now? Okay. Right. So as I was saying, for the test on 20th, you have to prepare up to this statement of work energy theorem, and in particular, the application of work energy theorem for systems which have springs and of course gravitational potential energy. Okay. So next week's lecture will be about revision and questions based on this. Okay. So please continue doing from questions from HC Verma also. Okay. So that's it for today's session, people. Wish you all the best.